Yes, it's working? Like this? Okay. Hello? Can you hear me? Yes? Hello. It's a great pleasure for me to be here. I am Ana Maria Rey. I am a faculty at the University of Colorado Boulder, GILA, and NIST. I am a theoretical atomic physicist, but I collaborate also very strongly with experimentalists. What I do is trying to understand how we can use lasers to control ultra-cold atoms, molecules, or ions. And the main goal is trying to use them for applications for precision measurements, quantum simulation, and quantum information. So the lectures that I'm going to give this couple of days are going to focus on alkaline atoms. Alkaline atoms, I'm going to tell you, they are currently the basis of the best clocks in the world. So they're reaching a precision that is unbelievable. But the idea is not what I want to tell you is that not only these systems are good as a timekeepers, alkaline atoms, but interestingly, the clock is so precise that the clocks are allowing us to explore rich many-body physics in a way that was not possible before. Or we have a lot of spectroscopic resolution to understand the behavior of many-body systems. And that's going to be basically the goal of my talks. I try to discuss a new type of physics that you can see in alkaline atoms that you don't see in alkali atoms. Before starting, just for myself, I imagine most of you are atomic physicists, or that's not the case. Yes? And if I ask you to raise your hand if you're an experimentalist. Okay, so a lot of experimentalists, that's great. Okay, that helps me to know how to target my talk. All right, so what is the agenda of what I'm want to cover? Well, I want to start today to give you a brief overview of alkaline atoms and atomic clocks. Then I'm going to introduce a little bit collisions in these systems and a new symmetry that these atoms have, that is SUN interactions. I'm going to try to tell you about density shifts in spin polarized gases and why we care about them. Then, I don't know, maybe today I will not be able to cover it, but probing SUN orbital magnetism, and for sure, not this lecture, but tomorrow or the third lecture about spin-orbit coupling. All right, so can you hear me well? Do you understand me well with the mask? I mean, if not, I will remove it. I mean, just let me know. All right, so let me start by introducing you what we mean by alkaline atoms. Alkaline atoms are atoms with two outer electrons, and therefore they're in the second column of the periodic table, as you can see here. But also there are others here in the lanthanide series, like ytterbium, that have similar atomic structure. So let me start by mentioning that at GILA, our favorite atom is strontium, and also for clocks, there is a lot of work in ytterbium. Although, among all of these, only calcium has been brought to quantum degeneracy, or BC of calcium. Then magnesium and barium, they have been Doppler cooled. And also mercury here, there has been also a lot of effort trying to Doppler cool. But if you want to see most of the work that is done to explore many-body physics, you most likely see strontium and ytterbium nowadays. All right, so just start by basic properties. So because these atoms have two outer electrons, then I'm going to try to, and the number of nucleons is what determines if an atom is a fermion of a boson. So it's clear because it's neutral. We know that the number of protons has to be even in these atoms. Therefore, the number of neutrons, if it's even or odd, is what determines if they are bosons or fermions. Yes? So therefore, because there is odd, means that there are fermions, and then even if there are bosons. So strontium 87 is therefore a fermion. And for example, the strontium 88 is a boson. Why we care so much about that? Because actually, because of nuclear properties of how the nuclear structure, how the nucleus is formed, actually nuclear theories has told us that systems that have even number of protons and even number of neutrons, they are forced by symmetries. I mean, I'm just know the rule. I don't know how to derive it, but by symmetries, these symmetries enforce that the nuclear spin is zero. On the contrary, because the fermions has odd number of neutrons, then it allows to have a nuclear spin degrees of freedom. So that's going to be key in this talk or in these lectures. So fermionics isotope has I larger than 0. And well, so for example, in the case of strontium, we have I equal to 9.5. That means I have 10 different number of nuclear levels to play with. Ytterbium, I mean, one of the most popular ytterbium atoms, for example, is ytterbium 173, that has I equal to 5.5, so it's spin 6, or six different levels. And ytterbium 171, well, it's just spin 1.5, so we have 2 levels. All right, I'm going to explain a little bit more. Oh, thank you. So I turn it on and off when, okay. All right. Now let me introduce a little bit the properties, the atomic properties of these atoms. So just a remind you, when I'm talking about the atomic structure, in general we use the notation Lj. Yes, for the atoms, where L is the orbital angular momentum, J is the spin plus L, and S is the spin degree of freedom. So for the case of alkaline atoms, what we have is because we have 2 outer electrons, what happens is that the lowest electronic level is the 1s0. So from that, you can see that this 1s0, sorry, I'm going to write large, just 1s0. This means that is a J equal to 0, of course L equal to 0, and is a singlet. This is the lowest energy state here of alkaline atoms. And then the first excited state is 3p0. So that has J equal to 0, it has L equal to 1, and is a triplet. Yes, makes sense? So why is that so important? Well, if you stare at these 2 quantum numbers, the 1s0 and the 3p0, you can see that this is J equal to 0 and J equal to 0. And therefore, this is a dipole forbidden transition by selection rules. So you cannot excite this transition. Moreover, this is singlet and this is triplet. That means it's not only dipole forbidden, but spin forbidden. And that's one of the reasons that these atoms are so useful for clocks, because this transition tends to be extremely narrow or totally forbidden. For the case of strontium 87, and sorry, this plot was actually like 3 months ago. I was copying from one thesis, and this is no longer the case. There was a very precise measurement by James Thompson group at GILA when it reported that actually the lifetime of this transition is 118 seconds. There's a line width of only millihertz, very, very narrow. On the contrary, for example, typical transitions that you can see in alkali atoms, so alkaline atoms are rubidium, cesium, the ones that are in the first column of the periodic table that you are used to, then you are going to see that this transition is both is spin and dipole allowed. And therefore, the line width of this transition is the order of hundreds of megahertz. So you can see that there can be 9 orders of magnitude different between this transition and this transition. Of course, this transition is useful for cooling and for many things. But the important point is that these atoms enjoy a very, very, very narrow transition. So now, if you are going to try to think of the utility of an atom, for example, for a clock, something that, you can always think classically, and you can try to identify this two-level system as a pendulum. And for a pendulum classical systems, you think about the quality factor, that is the ratio of the frequency at which the pendulum oscillates divided by the damping rate. So in these atoms, this is an optical transition. So the energy splitting is the order of 10 to the 14 hertz. It's an optical transition. Whereas, as I mentioned here, the lifetime is just millihertz. So therefore, when you compute this ratio, you get something, a number that is larger than 10 to the 70. So that's how good is this. So if then you think the analogy of a pendulum, then it would be a pendulum that when you set it to swing, it will swing for the entire edge of the universe. That's why these atoms are ideal for clocks. Yes? All right. So now maybe you might be wondering, but wait a minute. You are telling me that is dipole forbidden, spin forbidden, but I'm still talking about a clock. That's a little bit contradictory, yes? Because a clock means that you have to drive the transition to get the information. I'm going to explain a little bit more for how a clock operates, but in general, you are going to say, okay, there is something that doesn't make sense, how that can be. And well, the point is that for fermions, as I discussed here, we have nuclear spin. And that's what breaks what makes this transition allowed. Why? Well, the reason is that if you have a nuclear spin, you know that you have hyperfine interactions. And if you look a little bit, I was just showing a little bit only these two levels, but if you try to look at the details, at the fine structure, for example, of the different levels, when you look at it, you say, well, there is the 3p0 state, but of course there is also because this is, we have L equal to 1, so if you have L equal to 1, then in principle you are going to be able to have, if you have a triplet state, L equal to 1, and a triplet state, you can have 3p0, 3p1, and 3p2. Yes, they are there. And the point is that if there is a nuclear spin and you have this type of interactions, that the good quantum number is not I or J, but the good quantum number is F, that is J plus I. Yes? And therefore, these hyperfine interactions, and well, I have to admit also there is a little bit of spin orbit coupling. We are talking about two outer electrons. The combination of all of these makes the actual state TPP0, that is the one that the real state, not a pure TPP0, but it has a mixture of TPP1, TPP2, and 1P1. Why? Because, very simple, by perturbation theory, we know that if I, for example, our strontium is 9.5, if I look at the TPP0, it can have F is equal 9.5. But if I look at TPP1, then I'm going to have 11.5, 9.5, and 7.5. Yes, so this is going to be something, I'm going to be able to have the same F. And if you look at the state of the system just by perturbation theory, then you're going to have an admixture of the, for example, for TPP0, then you have the F equal to 9.5. But then the hyperfine interaction is going to couple also to, for example, TPP1 with the F equal to 9.5, and you're going to divide by the energy difference between the TPP0 minus the TPP1, for example. This is one of the. This calculation is very, very difficult. And requires a lot of elaborated calculations in order to compute them. What I'm just mentioning here is that actually is very important, and this admixture is what actually allows us to drive this transition. For example, what happens if I have a strontium 88 that has I equal to 0? Can I drive this transition? No. Well, in the experiment, they drive it by applying a strong magnetic field that mixes the levels. But in the absence of a magnetic field, this transition is completely forbidden. So, for example, in the case of 88, I cannot drive this transition, and I can drive this one just because this transition has some admixture of spin orbit coupling that allows it to happen. But for example, for this transition, we need a strong magnetic field. All right. So that's one of the important parts that tell us the origin of this very, very narrow line. So the other point is that as the G factor for the 1s0 and the TPP0 actually is going to be also a little bit different because of these admixtures. So this is a small, but it has dramatic consequence for clocks. All right. Okay. So, well, let me start by introducing you the simplest way to understand a clock. And this is very basic, but if you think about a clock, it has something that ticks and a counter that counts the ticking. This is just a pendulum clock, and that's the way to operate. So you have to count the ticking to determine time. So in atomic clocks, actually, it's exactly the same thing. So you need something that ticks and something that counts the oscillations. Now, what tick? In this case, is an electromagnetic wave. And what counts the oscillations are the atoms. So what is the difference? Well, the advantage is that the atoms have an energy spacing that is universal. Yes, so it's not going to depend on if any errors that we do with classical clocks. These systems are going to be immune to that. So these are just that's why time. Of frequency standards, the definition of the second is based on atomic clock, because cesium is the one that determines the second in the current definition of the SI unit for the second. So in this talk, we are going to talk more or about optical clocks. And the advantage between optical or microwave clocks, at the cesium is a microwave clock because the energy splitting is a microwave transition. Here we are going to talk about optical transitions that are much faster, of course, and if you have something that ticks faster, of course, it's going to be more precise. The issue is that the ticking of an optical clock is so fast that even electronics cannot record it. So in order to, I mean, of course, the atoms can, but in order to read it, we have to develop frequency combs that are able to compare between optical and microwave in order to read it. So that's one of the complications. But otherwise, well, optical atomic clocks, because operate with an optical frequency, then they're, in principle, they're more precise. And one of the, we are waiting that soon the definition of the S-high changes from being based on cesium to hopefully be changed for strontium or ytterbium. Hopefully this happens in the next few years. All right, so we have the source, we have the atoms, that is what are going to measure or recount the oscillation. But in order to do that, we need a feedback mechanism to measure the oscillations. And just to, let's see, now it's, yeah. So this feedback that allows me to lock my laser to the atoms is what is called Ramsey spectroscopy. So I'm going to start introducing that. And the Ramsey spectroscopy was first introduced by Norman Ramsey, and actually he won the Nobel Prize in 1989 for the introduction of Ramsey spectroscopy. So the idea of Ramsey spectroscopy is very simple. So I have a ground and an examiner. I imagine two-level system that are separated by some frequency different omega 0, and I want to lock a laser with frequency omega L to this transition. So basically, in very, very simple terms, the Hamiltonian that describes the system is going to be h bar omega 0 EE, and I'm going to have a laser. The Rabi frequency is proportional to the electric field and to the dipole moment of the atom. And then I have something that is sigma plus e to the minus omega L t plus sigma minus omega L t. Omega L t. So this is sigma minus e to the omega. So this is my Hamiltonian. So in order to do Ramsey spectroscopy, well, the first thing, just to start by very simple things, is that this Hamiltonian is time dependent. So we don't like to work with time dependent Hamiltonians. So in general, we go to the rotating frame, and to go into the rotating frame is just we want to do a unitary transformation. That is, the unitary transformation is going to go to a frame that is rotating with the laser. So I'm going to have something that is rotating with the laser. I mean, this is going to be sigma c operator here. So this is going to be my unitary transformation, and therefore I want to transform the Hamiltonian as u daga h u. So I think I put a minus sign here, and well, I mean, let me define instead. Effective Hamiltonian is going to be u daga this, but because this is time dependent, also I have to make sure that I subtract. Yes, I mean, you are familiar with this transformation. I mean, because I mean, if this is only if it's time independent, but because I have a time dependent, then I have to take account for that. And because we know that if I have the operator plus minus u, they're going to transform under this Hamiltonian, and is eta minus omega Lt. That's from a rotation here. Then from that, you can see that I'm removing the, plus minus. Plus for the plus, minus for the minus. And then if I do, and I try to write an effective Hamiltonian, then the advantage is that when I put this sandwich into u daga u, then the time dependence disappears, and that's what I wanted to. So if I put this, this part commutes with my u daga u, so nothing happens for this part. For this part, I just remove the time dependence because I'm canceling exactly the sign that I have in my rotating frame. So I get a Hamiltonian. The effective Hamiltonian, therefore, is going to be now the advantage of having the derivative here is that when I take the derivative, I'm going to have an omega laser here going down. So I'm going to have something that is h bar omega 0 minus omega laser EE. And then I'm going to have something that is just h bar omega half sigma plus sigma minus. So this is the in the rotating frame of the system, yes? And sometimes, and for a way that we want to handle this is that we define the detuning as omega laser minus omega 0. And I can regraph, this is EE, but I can compare this also to a Pauli matrix. So the effective Hamiltonian at the end is going to be minus h bar divided by 2. This is the detuning sigma c plus h bar omega divided by 2. And I can absorb the 2. Let's put the 2 here. Sigma x divided by 2. So I'm going to write it here. This is more clearly. So this is the detuning, and I have two parts. The part that is Sx, that is proportional to the Rabi drive, and the part that is the detuning. So the Ramsey spectroscopy consists on two parts. The first part is that I'm going to try to rotate my spin by applying a very strong pulse. So I make my laser I increase the intensity of my laser such that this term, this sigma x term, dominates respect to the tuning. So I can ignore the tuning, and basically I drive on resonance because omega is much larger than delta. And in this case, what happens is that I am going to apply a rotation. If I start with all my atoms in the ground state, then after I apply the rotation, for example, in this case, it's a rotation along the x direction, what happens is that I'm going to have, for example, depending of the time that I wait, or the pulse area theta is equal to omega times t. So if I have a pulse area pi half, then I rotate my spin along the y direction. So the component of the spin is going to have, if theta is equal to pi half, is going to be only at a y direction, but in general it's sine theta minus cos theta, depending on that. So then what I do is, I let the system, I want to, the idea is that I generate some coherences, and now I want to read these coherences by letting the system evolve in the absence of the laser. Yes, so that's called the dark time. And in this case, I turn off my drive, omega is equal to 0, and the only term that is in the Hamiltonian is the sigma c term. So, and then during this time, what happens is that my system is going to precess, for example, in the case of theta equal to 0, theta equal to pi half is going to precess in the xy plane. And then the expectation value of S minus operator as a function of this dark time is going to acquire a phase that is delta tau. And this is the phase that I want to read because that's what I know when my laser is locked to the atomic transition. So I let it evolve for some time, and then the only part that I need to do is try to read this phase, this accumulated phase. Reading coherences and phases is not easy. So what we do is we apply for example, a pi half pulse that, for example, transform SY to SC, and then I can measure populations. So after the second pulse, allow me to transfer this coherence or the phase accumulation into some population measurements that if I measure SC or I measure the number of atoms up and the number of atoms down, then I can extract this delta T, and that's how I can lock my laser to the atoms to the laser. So this is, that's called Ramsey fringe. So you can see that as a function of time, if I measure the number of excited atoms, for example, I'm going to see an oscillations versus delta tau. And this amplitude is going to be the contrast that, in principle, if I don't have the coherence, is going to be ideal. It's going to remain the same. It's always going to be, the contrast is going to be just this part, 1/2 sine theta, and if theta is equal to pi half, it's just 1/2. And then the fringe is going to tell me information about the phase is going to tell me information about the detuning. So that's the typical protocol that we use for clocks in order to lock the laser to the atomic transition. And Ramsey spectroscopy, is becoming a tool that is going to be, we are going to use it not only for locking the clock, but I'm going to explain, we are going to use Ramsey spectroscopy even for characterize a many body system. So, okay, everything clear with that?
Always there. And these pulses are another laser which you put on top to rotate, or
No. It's always that. So I use what I do is that I apply the laser only to rotate, and then I turn it off, and then I again apply the same laser to rotate the second pulse. Everything. My Hamiltonian is always this Hamiltonian. My Hamiltonian is always minus delta H bar delta SC plus omega, sorry, I always forget. This is always the Hamiltonian, yes? So I always in the rotating frame of the laser, that's important because this is the frame that I use, and I can turn on and off omega. And I turn it on only for the pulses and off during the dark time to let the system precess and accumulate a phase. Any other question? Okay? Okay. So this is the protocol and works fantastically for a single atom. Well, let me mention that for optical clocks, actually there are two leading type of clocks at the moment. The clocks that operate with trap ions and the clock that operate with neutral atoms. The clocks that operated with trap ions they operate with a single ion. Because it's very hard to control and have the ions repel because of the Coulomb repulsion and try to have the precision and accuracy that keep the precision and accuracy with two has been challenging so far. So far the state-of-the-art clocks operate with a single ion, and the most important, the leading ones are the aluminum and the mercury, and actually Dave Wineland got the Nobel Prize because of these clocks. So they have an impressive accuracy. So they have an accuracy of 10 to the minus 18. However, they have a little low stability because they operate with a single ion only. And let me ask you, do you know the difference between accuracy and precision? Can someone tell me what is the difference between accuracy and precision?
Accuracy is how close you are to the true value, and precision is like a variance of your measurement.
Yes, exactly. So the cartoon that I always use is that if this is the true value, for example, omega 0, this is the error, that's deviation from, this is the difference from accuracy, it's just the actual systematic error from actually determining the value of the transition. And this is the accuracy. And the sensitivity is associated with the statistics of your measurement. How reproducible are your measurements? I mean, yes, so this is the sensitivity. So what I'm telling you here is that trap ions have remarkable accuracy, but the sensitivity is not that good because it's a single ion. Mm-hmm. On the contrary, and that's why we are interested in neutral atom clocks, these are the leading ones, and the advantage is that the accuracy is at 10 to the minus 18 now, but moreover, we can trap in a single trap between 10 to the 3 to 10 to the 4 atoms. So they give me much more higher sensitivity. So the sensitivity is associated, or another way to try to characterize the sensitivity is the signal divided by the noise. Mm-hmm. And maybe this is going to be my, well, so if I have n atoms, mm-hmm, the signal is going to be proportional to n. Mm-hmm. And then what is the noise if I have n atoms? And now it depends if I have a product state or if I have an entangled state, yes? If I have a coherent state where I have an initial state, for example, that is a product over single particle wave functions, for example, a product of something like this. Mm-hmm. That means this state is pointing, if this is the wave function, this state is pointing along the x direction, yes? So then the signal that is going to be associated with the expectation value of Sx is going to be in half. And we know that on average, Sy is equal to 0 and Sc is equal to 0, yes? But because we have it's quantum mechanics and we have uncertainty principle, then expectation value of Sy squared is not 0. And it's the same that expectation value of Sc squared that is not 0. And instead, this is going to be proportional n2 divided by 4, yes? And before the noise, that is the standard deviation of that, then is going to be proportional to a square root of n. And therefore, the signal to noise scale like a square root of n. And that's why whole atom, we gain a lot by having many atoms at the same time trap. Mm-hmm. So that's why, well, in fact, the cesium clock is the one that is setting the standards. But it happens that even though, nevertheless, because of this accuracy and remarkable sensitivity, currently the strontium clock is the one that is leading, is one of the most precise. And for example, the clock at Gila that is run by Jun Ye, he has an accuracy and a sensitivity larger than 10 to the minus 18. And maybe this the number that sometimes he mentions, that is a clock that never gains or loses a second in 15 billion years. That is roughly the age of the universe, okay? So that's how precise this clock is. So that's remarkable. But now let's start to go to the many-body physics. So as I telling you, the advantage of the neutral atom clocks is that they operate with many atoms. Mm-hmm. So in principle, then the way that the clock operates is by trapping the atoms is in what is called an optical lattice. And I know that there is going to be a lecture in optical lattice, so I'm not going to enter the details. So this is a 1D lattice, so the two contrapropagating beams, what creates is a periodic potential for the atoms. So, I mean, they form a standing wave. So when they have a standing wave, two propagating beams, they generate a 1D lattice. So They generate a 1D lattice like the one I'm showing there, and the atoms are trapped in each of these lattice sites. Because it's 1D, along the other directions, it's just a Gaussian profile because of the dipole trap. So we have the atoms are trapped in a 1D lattice. In each pancake, we can have a lot of atoms, between 10 to 1,000, depends on what the experiment wants to do. And the idea is that, well, if the atoms all tick at the same rate, then we gain always, because we have a signal, as I said, that is larger. It's going to be n times larger than an individual atom. That is fantastic. But of course, it's never easy to deal with many atoms. And there are very important considerations that you have to take into account in order to design a clock based on that, the basis of a many-particle system. First, well, all the atoms need to experience the same Rabi frequency. I mean, in general, this is possible, but I'm going to explain you later, and I don't want to enter in detail at the moment. I want to say, yes, that's possible, but the fact that the laser is e to the akx, it means that the phase that the atoms feel in this pancake is going to be different than the phase that the atoms feel in this other pancake. So as long as the atoms do not, an atom here doesn't know the other atoms here, there is this kind of are independent. Well, we don't care too much about that, so that's not a big deal. But this phase, I'm going to explain later tomorrow. This phase is going to be essential also for starting to introduce what is called spin orbit coupling and try to do quantum simulation with atoms in the clock. This is one of the first concern, and we check. The other is that the atoms have to experience the same detuning. I mean, if the atoms feel different detunings, then it's not going to be a good clock. And if we think about possible detunings, one of the most important comes from Doppler shifts. I mean, we know that if I'm moving, I'm going to experience a different frequency. And that's why these clocks use a 1D lattice, and the laser that interrogates is along the very tight direction. So the laser that I'm interrogating the atoms is perpendicular to the direction where the atoms are almost frozen, because it's very tight confinement. So that's the 1D lattice is very important, or the lattice confinement is very important to prevent the Doppler shifts. But nevertheless, it introduces another decoherence mechanism, that is the fact that the ground, these are optical transitions, and therefore not necessarily the ground and the excited states are going to feel the same laser potential, because they can have different polarizabilities. They can have very different sensitivity to the laser that I'm used to trapping the atoms. So one of the biggest developments for clocks was the capability to identify what is called a magic wave lattice. A magic wave lattice is a wavelength at which the trapping potential for the ground and for the excited state is identically, because the polarizability at this wavelength is exactly the same for both. So it happens that for strontium, there is a wavelength that is approximately 100 nanometers, 160 nanometers, that is convenient, that Jung can generate the same trapping potential for the ground and the excited state. So this is another reason why this clock is so good at the moment. But the last part is that, well, we have many atoms, and the atoms are bumping into each other. And this is where collisions can actually significantly modify the ticking of the clock. And that's where many-body physics enters in a bad way, because it's at the beginning, Jung wanted to suppress any type of collisions. But it's going to be a win, because I'm going to tell you that the clock is so precise that even though Jung tried to reduce this collision as much as he could, he couldn't, because the clock is so precise, And this is one of the most important systematics in the clock. And I'm trying to explain a little bit the collisions next and try to tell you a little bit how we are handling and how this is opening a window for explore many body physics. All right.
May I ask a question?
Yes.
On the Doppler?
Uh-huh.
So is it somehow in a non-decay regime, or that's why there is no Doppler shift? Because we can imagine that you have a spread in D because of confinement.
Yes, but I mean, the important part is that the interrogation is perpendicular. I mean, the atoms are moving, the velocity is perpendicular to the interrogating laser.
Why is it?
Because the
I meant the velocity of the ground state of the lattice.
yes, but the atoms, I mean, along the lattice potential, the atoms are frozen. So there are three directions: the x.
Right, if you're speaking in the lattice direction, yes.
In the lattice direction, the atoms are so confined that they're only operated in the lowest band of the lattice. So there is no motion. So basically, the atoms are frozen at this lowest. I mean, there is an energy gap from going from here to here that is much larger. This gap can be of the order of 100 kilohertz. That is much more larger than the temperature that we operate. So
Somehow it's similar to the non-decay regime.
yes, exactly. We are in the lambda regime along this direction.
And even if it's at the optical frequency.
Even if it's an optical frequency, yes. K, yes. So in this case, K harmonic oscillator is going to be very, very small. It's much more smaller than 0.01. It's very tight. So we are operating at 300 recoils or something like that. Yes, that's key. And this is key also for, I mean, we want also to be in the lambda key to avoid tunnel. I mean, we want also a deep lattice to avoid atoms tunneling from here to here. So it's both to avoid the atoms talking between layers and to suppress Doppler shifts. No, perfect. I mean, please. I mean, this is so nice that we are in person. So please ask questions because I mean, being via Zoom is not ideal. So please ask, and so we can have fun. All right. Any other questions?
In the previous slide, you showed many neutral atoms for clocks, and you showed Ytterbium 171. Is it better than 173 for any reason, or just this?
Yes, 171 is better than 173 for two reasons. One is that it only have two nuclear spin states that is easier to handle and manipulate. And second, I'm going to tell you later, is because the collisions, the scattering length that is 0 for 171 for the ground state. So yes, there is one advantage of that. But mostly at the beginning, it was mainly because two states are much easier to handle than 6. Yes, please.
So here you're taking all have the same tuning, but there's no Zeeman effect.
This,
Why this is not written here?
the Zeeman effect, it's a great question. And the important part is that the way that they operate the clock is that you have 9½ and -9½, the two nuclear spins, and they can subtract and remove the effect because one is on the positive side, the other is in the negative side, and they take the average, and this is not a big deal. This is one thing. The second is that because and that's the other big advantage for clocks, is that we are operating at J equal to 0. This is a J equal to 0 state. So then the magnetic moment is not electronic magnetic moment, but nuclear. So these atoms are 1,000 times less sensitive to magnetic fields than alkali atoms, for example. So this reduces significantly the role of Zeeman shifts. So yes, so we operate this, at this, they interrogate this other transition, they subtract. And that's one of the systematics. They care very accurate, and they can cancel it very well. So I mean, there are other systematics, for example, black body radiation, and there are other think a lot. I mean, I'm being very simplistic here. Yes, so there are other effects that they have to put at least and reduce. But I think these were the worst, and that's what overcoming this was what gave an advantage to optical clocks. Well, because I mean, it's a very fast ticking, and if they were able to reduce these effects, as they were also able to reduce them in microwave clocks, that's what put optical clocks above the microwave. These are great questions. Mm-hmm. Any other question? Okay, so let me then enter the dilemma that I had when I was entering at GILA. This is where Jung was building his clock. So for Jung, he wanted better signal to noise, of course. I mean, so he wanted to pack many, many atoms in the clock. That's why he's using a neutral atom clock. But on the other hand, he knew that collisions are going to change the frequency of the clock. I mean, he knew that. He didn't understand the role of the collisions, but he knew that they could be bad. So, and in fact, when I was arriving to GILA, that he was starting to build his clock, he was seeing that there was the second largest systematic of the clock were coming from density effects. That means by changing the number of atoms in the clock, he was seeing that the ticking, when he was doing Ramsey spectroscopy, that the ticking of the clock changed as a function of density. And of course, this is terrible for clocks. I mean, you cannot change that. So that means that there was a very, very, very urgent need to understand the collisions in the clock. I mean, we want to move forward. And this is going to be this part of the task of these lectures. For me, when I was arriving to GILA and seeing that he was measuring density shifts, I had a smile because, of course, they were sensitive to many body effects. And then what I knew is that, I mean, in my mind, I mean, if you are a condensed matter, you think about condensed matter systems, and you think what makes condensed matter systems so complicated, but at the same time so exciting, is that they have to deal with the complex interplay between charge degrees of freedom, electrons are charged, orbital degrees of freedom, there are different orbitals, and spin degree of freedom. So the interesting part, and this is going to be, I mean, here I'm trying to summarize what is going to be the weight of this talk, how we are going to, how these lectures are going to be discussed, or the material. We have in alkaline atoms, we have a nuclear spin, I, for the fermionic isotopes. We have an orbital degree of freedom because we have the ground and the excited state. And even though the atoms are neutral, I'm going to tell you how we are going to effectively make them as charged using lasers. So we have all the three ingredients that makes condensed matter systems so exciting. So that's what I think quantum simulation with alkaline atoms is extremely, extremely rich. And well, no, I mean, so the idea is that we're going to try to understand the collisions to make the clocks better, but making better clocks also we are going to be able to measure very, very precisely the many-body physics. So it's a win-win overall. Yeah, okay. So yeah, so basically the clock is going to give us the glasses that are going to resolve a complicated many-body spectrum into very well-resolved lines, and we are hopefully understanding complexity in many-body systems. All right, so with that, let me start discussing in very simple terms collisions in ultracold atoms. So of course, scattering, you understand a particle scattering in a potential, or so something smashing and going out. In the case of quantum mechanics, I mean, we think scattering in terms of waves, yes? So basically, we go to the relative coordinates of the atoms that are colliding. So we have the interatomic potential B, and we see that in these relative coordinates, there is one incoming wave, and then this an outgoing wave, and we want to understand the properties of the outgoing wave. So very, very simple, in very simple terms, I have a wave function that has the initial wave that is propagating along e to the akz, because I'm choosing the quantization axis as being z, so it's a plane wave coming. Then there is the scattering potential, and then later when the particles leave the scattering potential, when they are very far away, then I have a scatter wave that is a radial wave, so it's AKR divided by R, but with what is called the scattering cross-section F. And if I'm able to understand the scattering cross-section, then I'm able to understand the collision properties of the system, yes? So the goal, when we talk about collisions or the scattering properties, is to determine the scattering cross-section. This omega can depend on theta, the angle, and also phi. But, and the idea is that if I know this f, the amplitude of f squared is giving me the cross-section that is at the heart of a scattering problem. So what we do to deal with the quantum physics of two particles? Well, we have two atoms that are colliding, and then instead of writing the coordinates of atom R1 and R2, what I do is a change of variables, and I define the center of mass coordinate, that is the average of the two, and I define the relative coordinates, that is the difference of the two, and then I define the reduced mass, that is m divided by 2 for atoms with the same mass. The two atoms are identical, and I define the total mass, that is 2 times m. M is the mass of the single atom. And I mean, you might remember that whenever you write the Schrodinger equation for two particles, you can always write it in terms of capital R and small r. And now the collisions only depends on the relative distance, yes, how close the particles are. So the collision potential is only depending of little r. So I have the part that is the kinetic energy of the center of mass, that is trivial, and I have the kinetic energy in the reduced coordinate. I have the scattering potential. I'm going to show you pictures of that. And then we have the energy. And the important part is this is a separable equation, so I can write my wave function as a product of the center of mass and the relative coordinate, and what I care is the wave function of the relative coordinate. That's the goal when I'm going to solve for a scattering problem. Okay, so I'm going to assume that the collisions, the potential is spherically symmetric, and because, I mean, in general, although there are potentials that are not like that, dipole-dipole interactions, I mean, in many situations, what the simplest case and the one that is more representative for the clock, for example, is when the potential is spherically symmetric. And in this case, we know, I mean, that the wave function can be written as a radial part that also depends on the energy, and because it's spherically symmetric, the spherical harmonics are good eigenstates of the system. So I can always write my wave function as a sum of L and M's. So this is the angular momentum and the projection along the z direction. And with this expansion, of course, the energy, I'm talking about the incoming wave and the outgoing wave, and I am assuming that the potential goes to 0 outside the collision region. So the energy can be defined as just k squared, the free particle, the single particle energy of a free particle, of this reduced particle. So it's k squared over 2 mu. Now, remember, I mean, I am going to work in spherical coordinates. So when I put for the kinetic energy, the contributions from these spherical harmonics gives me L plus 1 divided by R squared. And the first part is what gives me just the kinetic energy in terms of the radial coordinate. And well, I have the potential here and k squared from here. Yes, so I'm just putting this answer in the Schrodinger equation for a given L. And then, of course, I can, if I find a solution for a given L, I then can write a superposition. All right, so the potential for colliding atoms has always a characteristic form of a van der Waals potential in the long range. I mean, atoms are neutral, and so in general, because also there are, they don't have a net dipole moment. I mean, you have to induce the dipole moment of the atoms. The long range part of the potential is in the form of a van der Waals potential that goes like 1 over r to the 6, and the coefficient here in proportional to this is called the C6 coefficient. So this is in the long range, and this is the part that we care for the collision. Yes, there is a part that is where the chemical bonding happens that is really, really complicated, that there are some theories that actually are experts and help us to compute all this complicated spaghetti, of course. But as I'm going to explain, we in general don't care too much. And now there is the other term, so we have the potential, but you can see that the potential can be combined by this L plus 1 divided by R squared, and this is called the centrifugal barrier. And the centrifugal barrier is only non-zero for L larger than larger or equal to 1. Yes. All right. So the important part when you try to solve find a solution is that because of conservation of energy and because of conservation of particle number probability, after the collisions, I mean the particles come scattering and go away, the asymptotic solution of the wave function has to be the same up to a phase. That's what is only allowed by energy, momentum, and probability conservation. So all the information about the collision is going to be absorbed in what is called this phase shift at long range. So I have two quantities, this and this. There are two quantities that I can solve by using the continuity equation at the potential. So I have to guarantee that my wave function and the derivative is continuous, and I have two constraints that I can use to solve for these two. And well, there is a lot of algebra, so I'm not going to do it. I mean, have you seen scattering theory before in quantum? I mean, that's what I assume. So I'm just going to summarize and remind you the solution of the scattering problem. Because, I mean, the important part is that if you know C and you know delta, well, because you can always expand the scattering amplitude again in terms of L and spherical harmonics or Legendre polynomials, then the important part is that there's a unique relationship between the scattering amplitude for a given partial wave L and the phase shift. And you I mean, if you look at Sakurai, you can derive that easily by trying to match the boundary conditions and assuming that this is the asymptotic behavior of the wave function. But the key for this talk is that we are working at ultra cold temperatures. So we are always going to take the limit of very small k, zero energy, when k or the energy goes to 0. And in this, you can show that the phase shift divided by k has a universal form that has this form, where AL are constants, but these constants are what characterize the collisions. So in principle, they can depend on energy, but at low energy, there are constants. For L equal to 0, this A sub 0 is what is called a scattering length. And this is the only quantity that I need to characterize S-wave collisions. That means when I S-wave, I mean L equal to 0. When I have L equal to 1, then instead of the scattering length, I need what is called the scattering volume. You can see the AL, when L is equal to 1, you see that I mean, this is 2, and this is plus 1, so it's something that goes to the cube. And this requires to be like that way because actually, remember that it's a centrifugal barrier. So this centrifugal barrier means that if I am at low energy, the collision is going to be suppressed because there is a barrier that I have to tunnel across in order to collide. So that's why, even though the 0, L equal to 0 is independent of energy, the P-wave collisions are suppressed when by k squared, that is the kinetic energy, and that's why, of course, I need to have for dimension, I mean, to make everything consistent with units, I need to define a scattering volume. And these quantities actually can be measured experimentally, and that's what we care. I'm going to tell you later about the trick what we use in order to with these two quantities build the many-body Hamiltonian. Now this is the S-wave potentials, the potential for strontium atoms. So I have the case that is the potential for, this is the van der Waals potential here, the van der Waals tail for L equal to 0. And remember, I'm summing this up for L equal to 1, there is a centrifugal barrier. So for the case of strontium, for example, but it's similar for ytterbium and many other alkali atoms or alkaline atoms, this height, this barrier height is of the order of 30 microkelvin. And current ultra-cold atom experiments operate at microkelvin temperatures and below. So, that's one case. So L equal to 1 is suppressed by this centrifugal barrier. Now, the other point is that, and statistics matters, quantum statistics is fundamental. So you know that Pauli exclusion principle enforces antisymmetric wave function for fermions and symmetric wave function for bosons. And since L is the number that associated with the parity of my wave function, then if I have bosons, I must have identical bosons. I have only even L, 0 to, and if I have fermions, I have odd L. Yes, that because of Pauli exclusion principle, that's the only thing allowed by nature. So if I have identical fermions, then L equal to 0 is not possible. There are not L equal to 0 collisions. I mean, the other way that you understand is if you have identical fermions, the wave function needs to be antisymmetric, and therefore the probability of having two particles at the same time is same position is 0. So identical fermions cannot collide via L equal to 0 channel. And the only allowed channel for fermions, identical fermions, is L equal to 1 and viscous energy. So that's why when June was planning his experiment, he said, I want fermions. I mean, I am at microkelvin temperature. This is 30 microkelvin. I'm going to have suppressed collisions. I will build my experiment with fermions. And well, in fact, that's what he did. Now, I mean, let me try to, I'm mentioning that here A and B are the scattering lengths and the scattering volumes. And I'm going to tell you our theoretical approach to deal with them. And for that, we are physicists, and we use what is called the pseudo-potential approximation that for me is associated. I mean, I always think about this with the joke of a spherical cow. I don't know if you have seen this joke. The joke is associated with, there was a farmer whose production of milk was terrible, and he was trying to call people to help him. And he called a psychologist, he called an engineer, and he called a physicist. So the psychologist said, oh, please paint your walls with green, and you will make your cows happier, and they will produce more milk. The engineer said, okay, let's try to analyze what is the milking machine. Maybe it's not as effective. Let's try to improve that. And the physics started to analyze the problem, and they says, it says, who looked around the place and drew a spherical cow on the board, saying, let me consider a spherical cow in vacuum, emanating milk uniformly in all directions, and of course the farmer got completely confused. So for me, the pseudo-potential is that approximation. So the idea is that, as I told you, this short-range potential is so complicated. Only you need a very difficult numerical algorithm to compute them. So what we do instead? What we do is that, well, we have the real potential, and we are going to do the spherical cow approximation of this potential. And the only thing that I care is that I have the same scattering length, and because the scattering L is all what I care, then I'm going to try to match a potential that is very simple, is just a delta function or something very, very simple that is going to reproduce the same scattering length of the complicated potential. So, so in the experiment, they can measure A and B, scattering length or scattering volume. Anyone knows, for example, how to measure scattering length in an experiment? Like thermalization, because the particles are going to thermalize because of collision. So for example, if you have different temperature along, for example, you have a high temperature in one dimension compared to the other, then as a function of time, there is some time at which the gas thermalizes and become again spherically symmetric, and with that, you can extract, for example, the value of its scattering length. The other way that people do is with photoassociation, because what happens is that the scattering length and the energy of the last bound state of your potential are highly correlated. So if you measure the energy of your last bound state by photoassociation with a molecular state, actually you can extract the scattering length. And there are connections between the scattering length and scattering volume, as I'm going to tell you in more detail later. But the point is that we can measure them. So experimentally we have A. So if I have A, all what I need to create is a potential that actually reproduces this A. That is simple and I can manipulate. So I'm going to approximate this potential by something very simple. In general, when we work on collisions, it's better to go to momentum because of the scattering problem. As I was telling you, we have plane waves, and therefore momentum is the good basis. So what is easier to compute is actually the potential in momentum space. That is, you can do the Fourier transform and get the potential in real space. And I'm not going to derive it here, but I'm going to give you some notes. There is a way that I can reproduce some notes, yes, yeah. So, because, I mean, in general, I never was taught how to derive the pseudo-potential properly, and I think this is a simple and a nice derivation, but doing that in the Blackboard is going to take me too long time, so it's better that you read it, and if you have questions, you just ask me. So I'm going to give you some notes where I'm going to derive that this is an expression for the pseudo-potential. If you, it looks awful, but if maybe you, and you have to be very careful with regularization, but the information that is important for me, for you to know for these lectures, is that for S-wave collisions, the scattering length is just a constant, the pseudo-potential in momentum space is just a constant. It's very simple. It's characterized by the scattering length, the mass, and the volume is going to disappear when you are going to, I mean, if in momentum space is a constant, that means in position is a delta function, yes? And for P wave, the pseudo-potential is not longer a constant, as you expect, because it has to cause energy, but it has the form B cube and K times K prime. And you can see that makes sense because, of course, it's going to be suppressed at low energies. So these are the two key ingredients that we are going to have to insert this into the many-body Hamiltonian and try to understand the collisions.
Maybe I have to ask this earlier, but the scattering length is after the collision, I don't know, the length that the...
Well, physically, the scattering length is associated with a phase shift. Yes, so remember that I told you that delta L is all what, I mean, after the collision, when the wave function, I mean, I have my particles, they collide, and there is a scattering potential B sub R with very complicated form, but it acts as 1 over R to the 6 in the long range. But when the particles are really separated, they don't feel each other. So they come, scatter, and go away, go back. And then when they are far away, therefore, what characterizes the wave function just goes back to, it is just characterized by this phase shift. Yes, the effect or the phase that you acquire during the collision is set by this delta L. And this delta L has a one-to-one connection with the scattering length. So if you know the scattering length, then you know the phase shift and you can reproduce all the problem because, I mean, everything is known when you know the phase shift. there is a geometric implementation of the scattering length that is associated with the crossing of the wave function. The wave function at low energies is going to be 1 minus A divided by R. So it's associated when R is equal to A, is going to be when the wave function crosses 0. And it's associated with if you have, it depends on the bound state of the system. So it depends on the final bound state of the system, because you can have something that is something like that, or something that is bounded. Maybe I have a picture of that because I thought that maybe you would. I have a picture like that. Okay. It's not that intuitive, so that's what I've done. I don't elaborate too much, but the wave function at low energy can be written as in this form. It's a sine k. If you take, as I show, if you take the limit k very small, the sine k is just k. So this is the form remember. What I was written is sine square r minus delta L divided by k. Remember, look, I put the k outside. Yes. So if you have k small, then that's what is going to be associated with this, with this wave function. So now, depending of the nature of the last bound state, the scattering length is where it crosses 0, and it can be positive or negative depending of the character of the bound state. It's not that intuitive necessarily. So for me, for these lectures, it's just a quantity that determines how strong your collision are. So if the scattering length is very small, the particles are very weakly interacting. If the scattering length is huge, they are very strongly interacting. If the scattering length is positive, then the particles are repulsive. If the scattering length is negative, the particles are attractive. That's basically the information. Same for the scattering volume. Does that make sense? Okay. Yes. So yes, as I was saying, let's think about it just as a parameter, and that we can derive from the solving the Schrodinger equation, and this characterizes the pseudo-potential approximation. Okay, I'm going to give you the copy of these slides. Of course, this pseudo-potential go back to Fermi, to Huang and Yang. So it has been a topic of interest from many years back. And I will send you some notes on how you derived them. All right, so with that, I'm going to start now that we have the basic ingredients. I'm going to start to tell you more details about the collisions between alkaline atoms. And one very interesting property of alkaline atoms is that, as I mentioned, and that's why they're useful for clocks, is that they have J equal to 0. Yes, and as I mentioned, because they have J equal to 0, I dot J is equal to 0 to leading order. For the ground state is exact. For the clock state is not exact, but very small, the correction. So I dot J in general is equal to 0 for alkaline atoms. What are the consequences of that? Well, if you think about the collisions of the atoms, they are dominated by the electronic structure of the atoms, not by the nuclear structure. Yes, when the atoms collide, is the Coulomb repulsion, or is associated with the Coulomb or with the dipolar or van der Waals interactions that you have when the atoms are colliding. So remember, the potential that I was showing has the C6 coefficient that is only determined by the electronic structure. So the reason why the nuclear part enters in alkali atom is that they are never decoupled, because in alkali atoms, J is, for example, 1/2. Then J dot I is different from 0. You have a f that is j plus I, and f is the good quantum number, so nuclear spin is always involved. But if j is equal to 0, then there is no hyperfine. The electronic structure is completely decoupled from the nuclear structure, and therefore, in principle, the nuclear spin is not going to enter at all in the collisions. So, except from the Fermi statistics. So, I'm going to give you an example that perhaps you are familiar with, but just to make the point. Imagine that we have a spin 1/2 system, or this is at the heart of helium, for example. If I have two atoms, one spin up and one spin down, then I'm going to construct the fermionic wave function. The fermionic wave function has a spatial part that depends on the coordinates of the two particles and a spin part, yes? But I know that if I'm dealing with fermions, the function has to be totally antisymmetric because Pauli's exclusion principle. So if I have this, a singlet, yes, then the spatial wave function, because this is antisymmetric, this has to be symmetric. No other way around, yes? And I also have another function that I can have the opposite. This is antisymmetric. And this is symmetric. So now let's think about, for example, Coulomb interactions. Coulomb interactions only depend on the distance, relative distance between the particles, are completely independent of the spin, yes? And this is where this is going to be, the symmetry is going to enter. So Coulomb interactions, as going to happen, for example, in the case of alkaline air atoms, the interaction is completely independent of the spin. Nevertheless, because this function is antisymmetric, then we know that the interactions between the two particles is reduced significantly for the antisymmetric wave function compared to the symmetric. That is the idea of helium. I mean, this is the exchange interactions in helium. So, for example, in the simplest case, that how you write a most generic form of the interaction potential, for example, the H interaction for a spin 1/2 particle that has the properties that the interactions are completely independent of the nuclear spin, then, for example, you can write it as Bs R1, R2, 1, S dot S2 minus 1/4 plus Bp and R2. This is a minus sign, or plus, and I put 3/4 minus S1 dot S2. I don't know, hopefully you are seeing this part. So what is this telling me? If I'm a triplet, if I'm actually I should put triplet 0. Yes, no, that's good. So if I'm a triplet, S1 dot S2 is 1/4. So this term is 0. So, and it makes sense because the wave function, if I'm at a triplet, the wave function is antisymmetric. The only way, I mean, this is the part that is symmetric is the one that I can call IBI as wave interactions. So the S wave part of the interactions are associated with this term because it's only non-zero if I have a singlet. A singlet has S dot S equal to minus 3/4. So actually I should put a sign here. So if it's a singlet, this term is 1 and give me the collisions from the singlet state. Now, if here in this term, if I am a singlet, sorry, this is a plus. If I am a singlet, S dot S is equal to minus 3/4. So this is 0. But if I'm a triplet, S dot S is equal to 1/4. This is 1, and I collide with this potential. So what I'm saying is that even though the interactions are completely spin independent, nevertheless the spin can affect the magnitude of the interaction. But if you look at this Hamiltonian is SU2 symmetric. Why is SU2 symmetric? Because if I construct operators Sx, Sy, and Sc that are all the generators of SU2 rotations, this is the sum over sigma x1 plus sigma x2 divided by 2, sigma y1 plus sigma y2 divided by 2, sigma c1 plus sigma c2 divided by 2. You can see that this Hamiltonian commutes with Sx, Sy, Sc. So the Hamiltonian commutes with all the generators of SU2 rotations. So I think I should maybe start ending soon. Yes, that's so maybe what I'm going to tell you is that tomorrow what I'm going to derive is very similar relations, but instead of SU2, we're going to go to SUN. Because in alkaline atoms, happens that we have n internal levels. For strontium is 10, for ytterbium 173.66. So the interesting properties of alkaline atoms is that actually, because J is equal to I is equal to 0, the nuclear spin, the nuclear spin doesn't enter in the collision except the Pauli statistics, as I mentioned here, similar for SU2. And this introduces very important consequence. If you have a symmetry, for example, the system commutes, in this case with Sx, Sy, Sc, there is a conservation law. And the conservation law, in this case, means that if I have there is an SUN symmetry, and the conservation law is that I cannot change my nuclear spin when I collide. That means if I have particles red and orange, mean 9½ and 7½ after the collision, I cannot emerge in 1½ 3/2. This is forbidden, and I have to go back to the same, and I can have conserved my flavor. So this is a consequence of these SUN collisions, and this is going to simplify my life significantly because I'm going to only need a single scattering length to determine the interactions. So tomorrow we're going to go through it, and we're trying to understand what is the consequence of SUN symmetry and how we're going to use this symmetry to try to understand better the collisions in the clock. Any questions? Everything okay? Was the pace okay, or too? Yes? Okay. I'm going slow, but sometimes I think it's better to go slow than too fast. Or if I'm going too slow, you tell me. If I'm going too fast, please also tell me. All right. Okay. Thank you.